Hello all. Okay, so I'm going to try to get through the PowerPoint pretty quickly today. The homework is not that long at all. So let's get started. Today we're going to be talking about galaxy evolution. So it's going to be kind of similar to last chapter, chapter 20. Okay, now after we're done with this one, that means that's the two chapters, so it's time for another test already. So I'll post a review probably, and I'll probably give you the test next week. Okay? I'll keep you informed about everything just for now. Get this one done and the lab for this chapter done right now. Okay? So, here we go. Okay, so if I said this is how all the galaxies look today, I would hope that you would say that I am incorrect. Yeah, that's how all those galaxies look today to us, right? Because we took that picture. But remember, all those galaxies are at different distances apart from us. So they are all in different times of their life. And we are seeing them at different times. So some of those galaxies, like some of these ones that are like smaller, maybe they're really, really, really far away, and we're seeing it. It's 13 billion light years away or something, and we're seeing it as it was 13 billion years ago, right? So if you were to somehow magically appear to where that galaxy is, yeah, that small little galaxy, then it would look nothing as it does to us right now in this picture, right? Because that was 13 billion years ago. There's a lot of things that happened in 13 billion years. I mean, maybe the galaxy's not even around anymore. Maybe some alien civilization blew it up. I don't know what happened, but it's not what's actually happening right now, right? So, some galaxies. Now, this is the galaxy like formation thing. You're gonna want to come back to this to answer a couple of questions on the homework. But so you can see here, this is supposed to represent the beginning of our universe to where we are now. We're about 14 billion years old, right? Now, as you can see, this is galaxy formation. Galaxies that we see really far away, they don't have a shape. They're very irregular in form. We call them young galaxies, and some of them don't really get much of a form over that time. Maybe they didn't have enough gases to start forming out, or maybe star formation occurred really fast and rapid. And I'll explain right now why that might change some stuff. But something that you need to note on here is notice that spiral galaxies start taking their form after about 5 billion years, yeah? So I might be asking a question on that. So spiral galaxies take about 5 billion years to start seeing the formation on them. It looks about the same on ellipticals. Like it may be a little bit less time, but right around like the 5 billion year mark is when we start seeing the formation of those types of galaxies, yeah? And remember, we know this because we can look at this picture, we can determine how far away these galaxies are based off of the redshifts, and we can determine, oh, we are looking at that galaxy as it was 10 billion years ago. And then we see all of these different galaxies, and we can start categorizing them, how they form over billions of years. Okay, so on to the next thing. So how do we assume that these galaxies form in the first place? Okay, so we've kind of spoke about this idea a lot. It's very similar to how stars form. Giant gas balls were just uniformly distributed in space. Gravity pulls them together over time, and certain areas begin to be more dense than other areas. So one area that's more dense, like if you look at this is like a denser portion now, right? So certain gas particles are going to be more driven to go towards the denser part than maybe the less dense part that's over here. But if there's gas over closer to this less dense part and it's closer to it, it's going to be drawn to go towards it, yeah? So just gravity pulling gas together in a very random, chaotic way forms these gases. Some areas being more dense than other areas. Going on. Okay. We call the denser areas that are going to start forming galaxies in the future. We call those proto-galactic clouds. Now, that's not very random. We use that proto for beginning a lot in astronomy, as our previous uh, uh, chapters have told us. But proto-galactic, so beginning galaxy clouds, right? Proto-galactic clouds. Okay, what types of gases are these clouds mostly going to be formed of to create the stars and everything? You guys know the answer to that. Hydrogen, right? There's more hydrogen than anything else in the universe, and these are the things that create stars. Okay, so as these protogalactic clouds come together, there's certain regions in the protogalactic clouds that are more dense, and those gases come together, creating nebulas, right? And then those nebulas form mini stars, and you already know how that part of it goes because we've made models on it and everything. So I hope that makes sense. It's like the exact same idea as we were talking about with stars, and we're just making it bigger, yeah, to form galaxies. Okay, so why do some galaxies end up looking so much different than other galaxies? So like this one being elliptical versus that one being spiral. Let's go forward and find out. Okay, so it's probably gonna have a lot to do with the density of the clouds. Okay, now we're not 100% on this stuff here. There are different ways to make elliptical galaxies. Okay, we're pretty sure on the spiral galaxies they're loosely formed protogalactic clouds. Over time, the gases come together by angular momentum that's spinning. They kind of flatten out to make a disk, and then in that disk, stars begin to form. Yeah. Now, what we think might be different about the ellipticals is that, and here I'll explain it on this, and then I'll go forward to slides. What we think might be different with ellipticals is that maybe the gas clouds are more dense together, and so instead of gas spinning and angular momentum beginning to flatten out the gases, and then star formation occurs, we're thinking maybe the gas cloud is so dense that it creates all the stars at the beginning before it can spin and flatten it out. So you have a lot of star formation happening right at the start. And then since all these stars form very quickly, their angular momentum doesn't have a chance to begin to flatten out the disk. That's what we think. That's one of the ways that we think elliptical galaxies might be formed. Okay. So we just spoke about that. So we just spoke about this. Elliptical galaxies come from very dense protogalactic clouds, and the stars form before angular momentum can flatten out the disk, right? Okay. Now, what kind of really solidifies the idea of what I just told you is that a lot of very far away elliptical galaxies that we're looking at, we see them very red shifted. Okay, now why in the world would it matter if we see them red shifted and if they're very red in the first place? Yeah, because we see them very far away. They are redder galaxies and they are red shifted. Yeah, so the reason why they're red would kind of solidify or prove that thinking might be correct is because red would mean very, very old stars, right? There's smaller stars that live for much longer, and so maybe all the blue stars, the young stars, all died off very quickly, and there's no blue stars left anymore. Yeah, so that's what we think could have solidified that idea from that I was explaining on the last slide. Okay. Now, another thing that creates these elliptical galaxies I spoke about in the last chapter was collisions between spiral galaxies. Yeah, if you got two spiral galaxies and they collide, it spins all the stars out of whack, and they get drawn together from gravity, and they're not going to draw back together in a perfect spiral right at the beginning. So what you're going to get is you're going to get another new elliptical galaxy, okay? And one reason why we think this might be a way a lot of elliptical galaxies are formed is because we see elliptical galaxies in large groups of hundreds of thousands, yeah? They're very tightly bound together. So it could be that spiral galaxies were all colliding a lot a long time ago, creating these ellipticals, yeah? And the spiral galaxies we see in the very small groups, and they're not that close that they collide very often. Like we will collide with another spiral galaxy, Andromeda Galaxy, in about 5 billion years, yeah. But that I mean, when that occurs, we will become an elliptical galaxy, yeah. Over time, we will become an elliptical galaxy after that collision. Okay, now, I didn't say this here. Collisions earlier in the galaxy, in the universe, were more, you would see more collisions more often. And it only makes sense. Remember, we're talking about a universe that is constantly expanding. So right now, we're at the furthest we've ever expanded. Yes, because as more time goes by, we will expand more. And with expansion means more space in between galaxies, so they will collide less often. But if you drag our time clock back, we have a universe that's much smaller, and all those galaxies are compacted into that small little volume, so they're going to collide more often. So we saw a lot more collisions, or we would have seen a lot more collisions of galaxies very early in the universe versus where we are now. Yeah, so galaxies used to collide a lot more often way back in the day. And this might be why we got so many ellipticals sitting around, yeah? Okay, going forward. Okay, so collisions trigger star formation. Okay, when you have two galaxies, they collide. Well, you have a lot of gases colliding as well. You got a lot of these these gas clouds, these nebula running into each other, and it just triggers star formation. So you're going to see a lot of blue star formation occurring. Yeah, you can notice, you can see that right here in this collision because you see so many blue stars. Okay. So computer models show us that two spiral galaxies colliding will create an elliptical. Okay, so that's a lot of the support that we have for that theory, is that two spirals in a mathematical model, two spirals together make an elliptical. Okay. Okay. Shells of stars around a lot of elliptical galaxies, those could have been the the remains of a collision. So when these things collide, as you can see, many stars and things will be flung out to the sides. And so you can see a lot of shells of stars out here in the outer part of elliptical galaxies. And I explained this. Collisions may explain why elliptical galaxies tend to be found much closer together. Yeah, it only makes sense. If you're in a very close range, close vicinity, it's more likely that you're going to run into each other, right? Okay, so starburst galaxies. Okay, so what is a starburst galaxy? So starburst like the candy, yeah? So a starburst galaxy, what that is it's a galaxy that form stars very quickly, okay? And they form all their stars so quickly and use up all their gases that starburst galaxies are only around for about 1 billion years, yeah? And we see these guys really far away because they died very quickly. They only lasted about 1 billion years. So that's what a starburst galaxy is. Very quick star formation, using up all their gases, only lasts 1 billion years. Those are the three things you need to know about starburst galaxies, okay? Um, uh, Also, so supernovas, what could happen in a supernova? So if a starburst galaxy, what they're going to do is they're going to create a whole bunch of blue stars, young stars, that use up all their gas very quickly. Okay, and then those die very quickly as well, right? In about 1 billion years. There's a reason why we said starburst galaxies only last about 1 billion years, because that's how long very large stars last. Okay, when those big blue stars come to an end, they're gonna supernova, right? Okay, well, if a bunch of them are going supernova all at the same time, you're having a giant, lots of atomic bombs all exploding at the same time. And what that happens is it pushes all the wind, all the solar wind pushes all the gases away from the planet, and not from the planet, away from the galaxy. And so this galaxy now has gases so spread out that it doesn't have the gravity to bring it back together. So these starburst galaxies are like big stars. Yeah, they're made up of big stars. They use up their gas really quick. Then they go supernova and push all the gas away, and then they don't have the gravity to bring it back together. Okay? Okay. Okay, what would all this galactic wind do that would harm the galaxy from being around for a long time? Okay, so it's going to drive away all the gas so that it can't pull back with gravity, just like I was explaining in the last slide, okay? So, if the center of a galaxy is usually bright, we can call it, okay, so the center of many older galaxies that we see really far away, we call them active galactic nuclei. These are centers of galaxies that are very bright, okay? And we can have active galactic nuclei everywhere, okay? Anywhere, okay? So it's just a very bright center of a galaxy. And that's usually where the black hole is, right? So the brightest of these, I'm going to explain why the black hole would be bright, if that's something that's on your mind right now. Okay, so the brightest of these active galactic nuclei we call a quasar, okay? Now you're probably hoping you're wondering, if it's a black hole, why in the world is it bright? Okay, now here is what a quasar is. Okay, first off, it stands for a quasi-stellar radio source. That's how we came up with the word quasar. Okay, and we believe we're not really too sure exactly what a quasar is, but we're pretty sure that what it is it's a bunch of gas and stars surrounding a black hole, and the black hole's just sucking it all in. And so really what you're seeing is the light of all those things that are about to hit the event horizon. And so it makes it super bright. So it's not actually emitting this light, it's actually the light that is around it that's making it so bright. And these guys are like the brightest things in the universe, okay? And what we're going to find out here is we only find these things highly redshifted, okay? Which I hope you understand what that means. Highly redshifted would mean that it is very, very far away. So we only see quasars very far away, okay? So that would mean that they happen early in a galaxy's formation and not now, okay? Because we're only seeing them on things that are far away, meaning that we're seeing them on things that happened on galaxies a long time ago. Yeah? Okay, here's the luminosities of these things. They're greater than 1 trillion times the luminosity of our sun. 1 trillion times. That's a lot of times. Okay. And they come from areas smaller than our solar system. So these are small areas with lots and lots of luminosity. Yeah? Okay. Accretion of gas and supermassive black hole appear to be the only way to explain quasars, which I just told you guys. Okay, so what can we conclude about the fact that quasars usually have very large redshifts? They're generally very distant. Okay, yes, I just said that. They were more common earlier in time. Yeah, I mean, if we're only seeing them really far away, that means that they were occurring a long time ago, right? Galaxy collisions might start them up is probably what I was meaning to write. But all of these are correct, yeah? So maybe galaxy collisions are what caused these quasars to get started, yeah? Because we saw a lot of galaxy collisions earlier in the universe than we do now. Okay. We also see a wide range of electromagnetic spectrum that these quasars put out, indicating that we have a lot of wide range of temperatures of the matter that make them up. So all different types of stars and gases make these things up. So that's why we're seeing such a large spectrum. If it was only like very blue stars, we would see a spike on the blue, but we see spikes everywhere. So that's one reason why we say that it must be made up of a lot of different matter, and it's just sucking everything in, because it has a very broad electromagnetic spectrum reading. Okay, so next thing is radio galaxies. Okay, they contain an active galactic nuclei. Okay, an active nuclei. They shoot out jets of plasma, and these plasma jets emit radio waves. Okay, and they don't appear as quasars because they're being blocked by dust, but we assume that's what they are. Okay, that's what these radio galaxies are, but we can't see perfectly because there's a bunch of gas blocking them out. Okay, now how are these jets being formed? It's like the same thing as pulsars. Okay, you spin really fast and stuff flings out the northern and southern part of the thing that's spinning, and so here's the accretion disk blocking stuff from us seeing, and these are the large jets that are being flung out of plasma that are being flung out from the sides with radio waves. Okay. So that's how those are formed. Okay, now we've spoken about this a lot of times. Do supermassive black holes really exist? Yes. We've spoken of a lot of different reasons why. We see things orbiting around things that have no visibility. Like all these stars are orbiting around this point, and there's nothing at that point. But we know how gravity works, and we know there must be something. So we know that we call it a black hole, right? I'm gonna go past this one. Okay, so we believe that pretty much all galaxies have supermassive black holes at the center. And we're thinking that maybe all galaxies went through the quasar stage as well. Okay, so we know that they happen very early in galaxy formation because we can see them occurring very far away. So maybe all galaxies went through these things, and we can look at all the galaxies that we look at. We pretty much see black holes at the center. Obviously, we can't make it out on all galaxies, so we assume that galaxies all have black holes, and maybe they all went through a quasar stage, possibly way back early in time. Okay, so the mass of the galaxy's black hole, so the center black hole, will also determine how large the bulge of the galaxy is. Yeah, and remember the bulge is that middle portion of the galaxy that's not part of the disk. And I mean, that only makes sense. If you got a bigger black hole, then a lot more stuff is going to be orbiting around it, making the bulge of the spiral larger. I mean, that makes sense. Okay, last few slides. So quasars help us look at what is in our universe, okay? And how does it do that? So it does it through absorption lines, okay? And we spoke about absorption lines a few chapters back. So remember, a quasar puts out all types of electromagnetic spectrum. So it should be a continuous spectrum from gamma rays all the way to radio waves. We should see everything coming through. But if there is gases in between, like let's say there's these gases in between us and the quasar, this gas cloud will take out the types of spectrum. So like red light, if there's certain types of elements that use red light, those elements will steal the red light from that continuous spectrum the quasar put out, and we will see the spectrum with that red light taken out, yeah? And then we'll be able to match it up with the periodic table of elements and determine what that cloud was made of, right? That's how an absorption line spectrum works. So since these quasars are so far away and they emit all of the electromagnetic spectrum, and they travel so far through space, there's going to be a lot of clouds that block us in between, right? So because of these quasars, we can make out what's in the universe, okay? What the universe is mostly made up of. And we can even kind of determine what it mostly had in the past, what it has now, if it's different. We can do a lot of things with this sort of information. So this is just the slide pretty much explaining that, and that's the chapter. I hope you enjoyed. Send me questions if you're confused at any point in time, or we can set up a Zoom meeting, whatever you need. See ya.